This is the Daily Space for today, Thursday, July 2nd, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today, we are going to be joined by guest Dr. Matthew Graham. He is a Caltech researcher who was first author on a paper describing the discovery of a transient light phenomena associated with a black hole merger. This light lagged after the merger by several days and nicely matched earlier predictions of how black hole mergers can interact with their surroundings to shock things into glowing. Anytime a theory is found to be real is an exciting day, and we're super pleased that Matthew will be able to join us to discuss these results. Now, before we get to the interview, let's take a look at today's news. In today's top story, planetary scientists at Warwick University have discovered a super weird object that is best described as a planetary core from a former gas giant. Located 730 light years away, this object, TOI 849b, orbits a star not too different from our sun. The catch is its atmosphere was completely stripped off, leaving behind an almost 40 Earth mass core of rock density material. Today, this world is snuggled so close to its star that it orbits every 18 hours. And at this distance, it experiences its sun's every flare and outburst. According to the paper's abstract, the planet could have been a gas giant before undergoing extreme mass loss via thermal self-disruption or giant planet collisions. Or it could have avoided substantial gas accretion, perhaps through a gap opening or late formation. You can read the entire paper with first author David Armstrong in the journal Nature. To break that explanation down, they see three different scenarios as possibly producing this atmosphereless rock. Maybe it formed this way, and due to a lack of gas where it formed, it couldn't build up an atmosphere. Maybe this world had a horrible collision with other gas giants and lost its atmosphere during the catastrophe. Those are both fine examples, but it's the other one that is most tantalizing and most interesting to the researchers. This world could be the naked core of a gas giant that had its atmosphere blasted away by its star. This is a large object, nearly 40 Earth masses of just rock, and removing its atmosphere is non-trivial. But with such a small orbit, it's totally possible. This paper is a reminder that when we look at worlds today, we can't really know how they started. In devising solar system evolution models, we need to remember that worlds can start with amazing atmospheres and collisions, and possibly even other events like gamma ray bursts can all strip away those atmospheres. And then collisions with asteroids and comets can bring atmospheres back. The one constant of the universe is that everything is changing. And what we see today is just a snapshot of the changing cosmos. The dynamic nature of our universe appears in different ways in different objects. If you look at a massive galaxy cluster in optical light, you can often find evidence of, trauma. Gas and dust torn from systems, and galaxies deformed through close encounters with their neighbors. The true drama, however, pops out in radio light, where the trails of particles and tangled magnetic fields appear to shine. In a new data set on the cluster Abell 2255, a team led by Andrea Bouton captures all these effects in stunning detail using the LOFAR radio telescope. According to team member Gianfranco Brunetti, the filaments discovered by LOFAR could form exactly as a consequence of these turbulent motions. Another possibility that we are considering is that the filaments originate from the interaction between the galaxies, which move at speeds of many hundreds of kilometers inside the cluster. and the plasma that produces the radio emission of the halo. The degree of emissions from shock waves is something that we hadn't anticipated. Is something that we had anticipated, but this is the first study to look at just how far the radio emissions extend from this cluster. According to team member Reinout van Veeren, one of the goals is to understand if the radio emission extends also beyond Abell 2255, tracing the gigantic cosmic web that connects clusters of galaxies in the universe. When it comes to understanding our universe, everything we study needs to be considered in context. This means that when we're trying to understand the emissions from various sources, we also have to account for other sources changing those emissions along the way. This recently became particularly important for researchers trying to understand how it is that the IceCube Neutrino Observatory keeps observing unexpectedly large fluxes of high-energy neutrinos with none of the corresponding gamma rays that we expect to see associated with these neutrinos. According to team lead Kota Maras, high-energy cosmic neutrinos are created by energetic cosmic ray accelerators in the universe, which may be extreme astrophysical objects such as black holes and neutron stars. They must be accompanied by gamma rays or electromagnetic waves at lower energies. That means light at less blue colors, and even sometimes gravitational waves. So we expect the levels of these various cosmic messengers that we observe to be related. Interestingly, the IceCube data have indicated an excess emission of neutrinos with energies below 100 tera electron volts, compared to the level of corresponding high-energy gamma rays seen by the Fermi Gamma Ray Space Telescope. And this kind of a what the moment implies we either don't fully understand the origins of high-energy neutrinos, or there's something else involved. Neutrinos readily pass through material, while gamma rays can be absorbed by gas, dust, and other intervening material. So what is eating the gamma rays? In a new paper in Physical Review Letters, this research team describes how the environment around supermassive black holes can both generate the high-energy neutrinos and gamma rays, and then absorb the gamma rays into the surrounding accretion disk. Active galactic nuclei feeding central black holes and galaxies can produce the needed particles and have the needed absorbing material, neatly explaining a whole lot of previously confusing data. Science tends to work in two directions. We both observe things and then try to explain what we observe, like with the IceCube results. And we also make predictions about the universe and look for evidence of those predictions. Now, some theories are harder to believe than others, even with a profundity of evidence. And these are the theories I get the most excited to see prove true over and over again. From relativity getting tested to quantum mechanics getting tested, it is just pleasing when reality says, I know I'm weird, but I'm predictably weird. The LIGO experiments have just allowed one of these amazing tests of quantum mechanics to take place. It had been predicted that objects the size of LIGO's 40-kilogram mirrors would jiggle at the smallest level due to the constant popping in and out of existence of virtual particles. The amount that the mirror moves is a mind-blowingly small amount, just 10 to the minus 20th of a meter. Researcher Lee McCullough uses the following analogy to help us understand just how small that is. A hydrogen atom is 10 to the minus 10 meters. So this displacement of the mirrors is to a hydrogen atom what a hydrogen atom is to us. Thanks to the extraordinary preciseness needed to measure gravitational waves, this amount of noise is apparent in the LIGO data and nicely matches prior predictions, showing once again that with science we can understand things that our day-to-day experiences never prepared us for. Yes, folks, quantum mechanics is still true. And this result circles us nicely back to LIGO and our guest for the day, Dr. Matthew Graham. In just a few moments, we'll be discussing how a black hole merger can kick things into shining. I do need to do some camera changes and make sure everything's up and running. So while I do that, I'm going to stick the please stand by video up. So please, well, stand by, because we're going to be right back with some really cool science. See you in a moment. Hello, everyone, and welcome back. I am now joined by Dr. Matthew Graham, a Caltech researcher who I've had the pleasure of knowing for many years. How are you doing today, Matthew?
I'm doing very well, thank you, Pamela, and thank you for inviting me on this morning.
So this is just one of those cooler pieces of research, and I want you to tell the story from your perspective. How did this unravel getting to this research paper?
Right, so, as you're aware, one of the things I'm really interested in is how those supermassive black holes that you were talking about in the news section, how they vary with time. And we study them with both ground-based telescopes and satellites to try and understand what that disk of gas, that accretion disk, is doing. And a few years ago, we thought we would try and identify these really extreme flaring events, the things that involve them brightening many, many times, just to see if we could catalog that behavior in the big data sets that time domain surveys are producing. So we have various telescopes around the world which are looking up at the night sky every night. And we now have, 10 years worth of data of any region on the sky, and we can see how it's changed. So we look at the supermassive black holes, and we found that out of maybe 500,000 that we know about, 1 in 10,000 of them showed a really big flare. This is, something that lasts maybe several years. And this was back in 2017. And we tried to think of various different physical explanations for this. It's obviously something unusual is going on in the disk. And we thought about maybe it was what we call a tidal disruption event, which is when a star in the disk gets too close to the supermassive black hole in the middle and gets pulled apart. And that's the sort of thing we see. So that's maybe one explanation for these. Maybe it's just a star going supernova in the disk. Another big explosion dumps a whole load of material onto that supermassive black hole, and so you get this flaring. It was 2017, LIGO had just started its second run. Everyone was looking for neutron star mergers, compact object mergers. And so we sort of said, maybe it's one of those happening in the accretion disk. And I'm very fortunate that two of my colleagues, Barry McKernan and Savik Ford at City University, New York, and the American Museum of Natural History, are theoreticians who've thought about this for at least the last 10 years. What happens if you have stars really close to that supermassive black hole, and the products of stellar evolution, so when they become neutron stars and black holes. We think that most galaxies have a supermassive black hole in the middle. The Milky Way has something that's like, I think it's about a million solar masses in the middle. But we also think that there's a stellar cluster, a star cluster in orbit around it, very close in. And maybe there's even something like 10,000 stellar mass black holes very close to the Milky Way supermassive black hole. So if we sort of think that's happening in our average galaxy, that must be happening elsewhere. And so what happens if you have all these things moving around and two of them merge? What do you see? So this is a very different environment from just regular empty space. We're talking about a very dense, rich gas disk with this supermassive black hole somewhere nearby. And we put a paper out last year, a theoretical model saying, well, we think there are a couple of physical processes that could go on, which might give us a visible signature from this if we see this. And we thought, well, okay, LIGO 03 had started last March, and I'm the project scientist for one of these new sky surveys called the Zwicky Transient Facility, which is run out of Palomar Observatory. We used the same 48-inch telescope that Zwicky developed in the 1950s for doing
a new camera.
With a new camera, yes. So, but it's a 70-year-old telescope,
Yeah.
but it's been updated all the time.
Yeah.
So we now have 16 CCDs on it, and we can cover about 48 square degrees per night, per image rather. So we can do 4,000 square degrees in an hour. So we can cover large areas of sky very rapidly. So this has been used a lot for a lot of the follow-up of LIGO triggers when they're looking for neutron star, or neutron star black hole mergers, which we did think gave you a visible flare. And we discovered one of those in 2017. Well, lots of people discovered it in 2017. And but the difference there is what typically happens is LIGO trigger comes out, and rapidly half the telescopes in the world suddenly focus on the area they've said, we think we've detected something here, and they're all looking for it and whatever. That's because these killer novae events, the sort of things that those sort of mergers of compact objects produce, are very immediate. Our model, on the other hand, because this is all happening embedded in this big gas disk, it actually takes time for the process to happen and for the photons that are produced to make their way out of the gas disk and for us to see. So we don't need to move immediately. We can wait a few days or even a few weeks and just keep monitoring that region of sky night by night, as we do with our regular sky surveys. And if we see something interesting, we can say, that could be, it's the sort of object we think it is, and start following. So about the end of last year, LIGO had put out enough events that we could do a reasonable search. And we also had enough data past each of those events where we could search through. So we went through looking for this particular signature that we were interested in. That is the production of, what happens when those merged black holes interact with the accretion disk. And, okay, find those which are in the right area, the right distance, find those where they've had a flare within the right amount of time after the LIGO event. Okay, that whittles it down to a handful, and then you got to go, right, okay, well, what else could these be? Is this a supernova? No, doesn't look right. Could this be gravitational microlensing? You have something passing in front of the quasar and it brightens suddenly. No, timescales are wrong. Could this be a tidal disruption event? No, it doesn't look right. Okay. Could this just be regular AGN activity, active galactic unit? Because we know these vary. We've known they vary since they were discovered in the 60s, and it's one of their characteristic behaviors. So, but we have detailed mathematical models of how we expect that behavior to be. And so when you characterize the behavior we see in this particular source from the long-term data that we have for the last 15 years, it's been doing some stuff, but it hasn't done anything like this. And then we go, okay, so this looks unusual for this object. Let's look at a larger sample of quasars, active galactic nuclei, how they varied. Actually, very few of them seem to have varied like this either, with this sort of particular flare and this sort of thing. So this becomes an interesting object in that it's unlikely to be regular quasar activity, regular AGN activity. And so because it matches what we think we're looking for, you sort of go, this seems like a plausible candidate. And when we start fitting the model and looking at the parameters involved, this looks to be an interesting event from the LIGO perspective as well, because it looks like it's on the more massive side. So that the stellar mass black holes that have merged puts this into the sort of 100 to 200 solar mass range, which is
big.
It's big because you can't get an initial black hole of that size typically from a star-going supernova. It actually has to have formed by a previous merger of smaller black holes to get up there. And one of the interesting things about our model is saying that you have to have preferred environments for that sort of thing to happen. It can't happen in regular space. There's not enough time for the black holes to meet and meet more black holes. But if you have a supermassive black hole nearby, that gives you a very deep gravitational potential well, which draws everything into it. And if you have all these other stellar mass black holes nearby, they're going to be drawn into a closer environment, a more dense environment. So they're far more likely probably to merge and merge and merge and merge and give you this environment. So the fact that we found seemingly a more massive merging system in the accretion disk still matches what we predict from the theory. So this is, it's another validation. Now, the flaring happened. We expected some sort of spectroscopic signal potentially. Unfortunately, because we made the discovery about 180 days after the gravitational wave, and by that time the flare has died down, and the spectroscopic signal we also expect to have died down. So we used Keck in early January, one of the Keck telescopes in Hawaii, to get a spectrum, and it looks exactly the same as it did 15 years ago when Sloan observed it, which is good, because it also meant, it meant that there were no unusual spectral signatures in there that may come from a late time supernova, for example. Yes. But it also meant we couldn't see one of the things we predict in our model, which is that the line profiles in that spectrum shift slightly. Now, the big prediction we do make is what's happened is that those two stellar mass black holes, when they merged to create that new black hole, it was given a kick from the emission of gravitational waves in the final moments of the merger. And that kick is out of the plane of the accretion disk.
Is it always in that direction? This is one of the things.
No, it's a random direction, somewhat, but it's not. It's never. It's typically out of the plane and not in the plane. So it gets kicked out. Now, it's still gravitationally bound to that supermassive black hole, so it's actually still in orbit about it, but it's now at an inclined orbit to the accretion disk. So that means it's going to go out and then interact with the accretion disk again in a year and a half, 2 years, something like that. So what we expect to see is a second flare, if our model is correct. We're going to be looking at the end of this year and next year. We would expect to potentially see a second flare as that black hole goes through the disk again. And that would be, so we have a prediction, a testable aspect of our model. Now, if we don't see the flare, we maybe have to rethink our model or rethink why we didn't see the flare, or, but it's an interesting prediction. So what's really exciting about this, however, is, as you've said, it's very unusual to think you might see a visible signature from a black hole, which is supposed to be, no light doesn't escape from it. LIGO finds a lot of these black hole mergers. It hears them.
Yeah.
And what we essentially have done is we've now seen this, but unlike a thunderstorm where you see the flash first and then hear the thunder, we've heard the thunder of the gravitational waves first, and then we've seen the flash. Just because the mechanism is slightly different, it takes time for the light to come out. But this is really cool, because it opens up studying accretion disks and sort of supermassive black hole regions to using both gravitational waves as a probe of what's happening actually in the disk. because we can't see in because it's all embedded, but we can hear what's going on now. And then we see the visible flash, and combining that information now tells us about that environment, how rich it is, how dense it is, how thick it is, stuff like that. So for people like me who study, quasars and how they vary, this is very exciting. But this also hopefully tells us about black hole mergers, which is exciting for people who also, how do we get the intermediate mass black holes, and how do we get those supermassive black holes, and things like that. So we were very, very happy to see this,
And
but it was unexpected. It was unexpected.
and this is really database research at a certain level. Just
Yes,
how accurate is LIGO in giving you positions on the sky?
it's so. This is yes. That's a very interesting question. It's not currently. So what we talk about the localization region,
Hmm.
which is the area where LIGO is 90% confidence that this event has happened in,
Yeah.
and that can be 1,000 square degrees or larger for a black hole merger. For a neutron star merger or neutron star black hole merger, they're much larger. They're sort of 5,000, 10,000 square degrees in some cases. So that's why telescopes like the 48-inch at Palomar is great. We have that large field of view. We can just go snap, 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 and we can cover this area in half an hour, say. But the advantage with this type of event is we don't need to do that because we're doing archival. We can just do our regular surveying, and we can monitor that region on the sky because we will observe it once every 3 nights, typically with the ZTF. And so this means, 30 days, 60 days later, we can say, okay, which of those objects that we know have a supermassive black hole in the middle and is active in that region? Okay, that's 3,500 objects in this particular case. Which one of those did something interesting in the last 60 days? That one did. And so and going forward, LIGO is now offline, and they're upgrading it for 04, which starts in about a year and a half time. Our plans for 04 are we will be able to monitor much more in real time. LIGO event comes out hopefully with a smaller localization region, more accurate positioning on the sky, and the distance. And we're trying to convince them to give us some more information than they currently give us as well, because LIGO doesn't currently, when they release their information, in the sense that we've detected something, they don't tell you how massive those stellar mass black holes are. So we had to do a sort of back of envelope calculation when we're recreating what we think we found. If LIGO gave us that information out already, then it means we can be far more precise about what we would expect to see. So, if it's 2 5 solar mass black holes merging, maybe we won't see it. If it's 2 50 mass black hole merging, we probably would expect to see it. And sort of being able to have that sort of information as well will make it much easier to figure out which things we should be tracking, to the extent that because we also know roughly what the mass of a lot of those supermassive black holes are, we can even figure out beforehand the subset that we should be observing, because we think we might see something if there's something in that area. So I think going forward, there's a lot of interesting things we can sort of plan and think about based on the information we already have in hand, and also what they may be able to provide us with in the future. And so find far more of these things if our model is correct.
And what I love about this is it's essentially taken observational astronomy and reduced it to a software problem of,
Yes.
if LIGO detects blah in this region of the sky, do a filter on objects that match these characteristics and then identify ones that underwent a transient phenomena in this time window.
Yes.
The reality of coding it is a bit more complicated because processing data adds a lot of noise to things. Nothing is perfect. You don't know exactly when and where, but it's a software problem.
Essentially, yes. So this is the advantage. So, and it's a software problem because, you have so much data. But in a sense, you can think of it, it's always, this sort of work has always been a software problem. You know, back in the 1920s and the 30s, when Hubble was looking for variable stars, or in extragalactic systems, or when Clyde Tombaugh was looking for, and Percival Lowell were looking for Pluto, they're flipping between photographic plates using software in their head to say, oh, that thing's moved. Now we digitize all our images, we put them into a computer, and we say to the computer, tell me what has changed from night to night in these regions. And so so the activity is an old activity. We're just using very modern tools for it.
And this is one of those problems that is a version of the three-body problem, which makes it completely crazy fun in other numerical sorts of ways.
It's actually even worse than that.
Okay, go ahead.
Well, so it is the three-body problem. You have a supermassive black hole there, and then you have this very rich accretion disk of gas around it, and you have a merger which is some ways asymmetric potentially, and so you then have something which is accelerating very fast through this very dense medium, potentially with jets, and in this strong gravitational environment as well. So the simulations aren't there yet to match what we think we've seen, which is why there are questions on a more technical level about how accurate our model is and things like that. But what's really interesting is, we can maybe say things about that, but it is, as you say, it's just a horrible, horrible problem to model it, and you need the full general relativistic magnetohydrodynamic blah 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 things to do it, plus this sort of thing. So it's hard to do, but we're hoping that there are people who are interested in this and may model it in the next few years. So again, we also then end up with a much more realistic idea of what we would expect to see, because the model that Barry and Savick came up with is, it's a little more sophisticated than the back of an envelope, but it is, it's sort of, if we assume basic physics and it does this, then we should see this shape, which is great, because that's exactly gives us what we're looking for. One of the issues often with these heavy numerical simulations is they tell you what the mass transfer, what the gas lumps might be doing, but then they don't translate that into what the observer may expect to see, because doing all that radiative transfer stuff is very difficult.
Yes.
So, here at least we know it should be this sort of shape and then this sort of shape. And that's exactly what we need to go through the data and say, right shape, wrong time, wrong timing, right shape. Oh, this looks right.
Now,
there's a candidate.
You were very careful in your language to say that the black holes triggered the emission of the light. And that when the black holes plunge back into the accretion disk in a year or so, and I assume that you're getting that based on estimating the distance from the supermassive black hole?
Yes. So we sort of think, to give you some idea of scale, if we think that the two merging black holes are about the size of a pea, about a centimeter across, then they've merged into something that's about the size of a peanut.
Okay.
But they're going around a supermassive black hole, which is the size of Manhattan. And this gas disk goes from New York City out to about a quarter of the way to the moon. Okay, so we've got these peas going around Manhattan, and they've merged at roughly where Miami is from New York.
Okay.
But the disk there is about 50 miles thick in comparison to these little pea-sized things. But they're traveling at 125 miles a second as well as the other thing. So the dynamics of the system are huge. Yes, but they're merging relatively close in to that central massive black hole. They're actually about 700 times the radius of that central massive black hole out. And this accretion disk goes way, way, way out. So it's actually very close in comparatively on these massive scales to that supermassive black hole.
Now, I was going to ask you, what is it that causes the light? I feel like it's more accurate to ask what doesn't when you have these kinds of dynamics taking place. Can you give us some broad descriptions of the effects that are causing these black holes to make the accretion disk light up through their passage?
So so what's happening is that the when the merger happens, gravitational waves are coming out, but that final burst of gravitational waves at merger gives a kick to the new merged black hole, and it's that kick that it's given. It's just transfer of momentum, and everything has to balance out. And so you've got the gravitational waves going this way, and so this gets kicked this way. That gets kicked, and it's because it's a sizable gravitational mass in its own right. It has its own little sphere of influence, like the moon is bound to the Earth. It's within the Earth's sphere of influence, and that gets dragged along with it. But it's plowing into this much richer environment. And so what you get is initially you get a shock front building up as this thing's plowing up, and that shock front heats that gas. And so that's the initial rise that we see from the flare.
And hot gas gives off light.
Hot gas gives off light and gives off ultraviolet light and potentially gives off X-rays, depending on how hot that gas is. So we might expect to be able to detect this not only in the visible range of the electromagnetic spectrum, but also potentially in ultraviolet with the Swift satellite, or maybe even X-ray, depending on how energetic it is. And again, that's dependent on velocities and mass of the system and stuff like that. That material that's initially bound, because it's moving through, actually gets stripped off. Okay. And so you then have that stellar mass going through, but it's still moving, and it's a massive system, and it's getting new material, building new material onto that. And then that gives you a second brightening. This is just what's called Bondi accretion onto that. But eventually that black hole will leave the accretion disk, as we say, because the kick is out of the disk and not necessarily in the plane of the disk. And that material all falls away, and then you have a relatively quiet black hole just in orbit, and that's when the flare dies down. So it's this initial, it's the motion through the disk, initially the shock front heating up the thing, stripping away, and then material falling, getting dragged onto, and getting heated up as it gets accreting onto that stellar mass black hole, in the same way that you have this big accretion disk accreting onto the supermassive black hole nearby.
And so one of the awesome things about black holes is the physics is the same at all scales.
Yes.
Take a 3 solar mass black hole, not that we've necessarily found one, we might have, but take a tiny one, take a 3 billion, and you're going to have this same dynamic set of events with the magnetic field, the jets, the accretion disk. And so here you can have a case where it's essentially black holes all the way down.
Yes. And in fact, you're absolutely right. So we have 100 solar mass black hole here doing its thing, next to 100 million solar mass black hole doing its thing. So it's, here's granddaddy and here's grandson, as it were.
So I'm going to look at some of the questions we have coming in from the audience. Please. So Raj Luthra is saying, is there a limit to how big a black hole can get?
That's a very good question. What we've found from the galaxies and the supermass black holes in the galaxy is that it's probably around 10 billion times the mass of the sun seems to be the limit. Now that's probably just because the age of the universe is currently such there haven't been enough mergers of galaxies to create that. We know that our galaxy and the Andromeda galaxy are going to merge sometime probably in 4 or 5 billion years time. And when that happens, the supermassive black hole at the middle of the Andromeda galaxy and the supermassive black hole in the middle of the Milky Way will merge to create a bigger supermassive black hole. So it's probably just there haven't been enough merger events to create anything bigger than about 10 billion. But fundamentally, there's no reason why, that we currently know anyhow, why you couldn't have, and there is this old theory that maybe the universe itself is a black hole and we're living on the inside of it. And, It's super massive. But no, there's no limit beyond the amount of time that's happened for these events to happen, because these black hole mergers, even in something like the accretion disk, where it may be relatively common, it's still maybe once only every few million years or so. And the big merging systems are much rarer, because that requires galaxy collisions.
One of the things I'm really enjoying as we're starting to see more and more systems at high redshifts is this realization that supermassive black holes form both through the merger of objects and also, in a few cases, from just the complete collapse of massive
Yes.
clouds of material early in the universe. And those initial formed through accretion black holes seem to possibly have their own cutoff point where the system around the supermassive black hole that's feeding gets so bright that it empties the
Yep.
surrounding region.
Yep.
So it seems like the black holes will turn themselves off with light, essentially choking off inflow. But mergers are always possible.
Yes.
And I love this. There's multiple ways to grow a supermassive black hole.
Yeah. Yeah. Ultimately, you can't win against a merger,
It
because
yes.
the gravity will just eventually draw them together. It'll take a long time, but there's another, there's what's called the final parsec problem with the supermassive black hole binaries, and how long it might take them to merge, and maybe there's some mechanism there, but that's a separate talk.
so so Sarah Huckham asks, if the event data arrives in the 2 days not looking at that part of the sky, can you still get at the event? So how long does this flare last? Do you have to
Yeah,
worry about
so if you want to show, I think it's one of those little pictures I sent you, which
um
actually, it's the one marked figure 1.
not figure one. All right. So
It's the red, green, and blue curves.
oh, that is figure one.
Yep.
Okay. Yeah, let me pull that up. Okay, it's on the screen.
Okay, thanks. So this is the data from ZTF. The green. So we observe, this survey. We observe in 2 filters. We observe in a green filter and essentially a red filter, in the visible. And then the blue at the bottom is the difference between those, because that color information tells us about the temperature of the disk and the gas that we're looking at. So this is data from, about the last 2 years. That vertical dashed line is when the LIGO trigger went off. And as you can see, this object was doing nothing, burbling along, and then the LIGO event happened. Then about 30 days later is when it started rising up. The flare happens and it decays, and the whole thing lasts about 100 days. So even if we don't get it, so it's because it's about 100 days or so in length, it means we'll get some of the data through observing, and it's actually rare for us to not be on sky for any period. We've lost occasional weeks worth of data because of bad weather, particularly in the winter. You get
Yeah.
one of these. We lost about 3 weeks at the start of this year, because there was just successive Pacific storm after Pacific winter storm after Pacific winter storm. So the only things that really hit us tend to be Pacific winter storms and wildfires. But those 2 things aside, we're on sky every night. We've been on sky taking data through this whole lockdown, because the telescope is robotic. So COVID-19 hasn't affected us in that regard anyhow. But no, so we may miss the start if we're monitoring and writing it, but we'll get it 3 days later, and then it'll be even more obvious if it's flaring up or not.
And 100 days is a gloriously long period of time to be able
Yes.
to, as long as you catch it, which you're going to do on the next run of LIGO, uh, during that bright phase for spectroscopy.
Yes, absolutely, absolutely.
So
Uh,
Aristro asks, is this how you build intermediate mass black holes?
um, it's one of the models, and it's probably the most viable model. Um, to get those intermediate mass black holes, you really need some sort of a hierarchy of previous mergers. Um, and there are very few places, as I said, that can happen. If it happens in regular space, you may be lucky enough to get a single merger, but then the density is too small and the chances of meeting another black hole are too small and it takes too long. In these really, these deep gravitational wells, you can have far more mergers and do this buildup. And actually, what happens as well, you even within the accretion disk, you end up with a preferred region where some of the black holes may be, and so you can end up with there's a more massive one than the other ones, and it just keeps swallowing the smaller ones and smaller ones, building up to an intermediate mass black hole, which
And
is about 1,000 stellar masses, we sort of think, or larger.
and this is where you have to start worrying about things like black holes ending up in resonance with one another and flinging
Yes.
things in all directions. And
Yeah. Yeah. Stuff that's really interesting for people who do numeric relativity calculations.
so this work has required you to deal with relativistic equations, dust, magnetic fields in a hydrodynamic system. Was there any of the hard parts of astronomy that you avoided?
No, but this is the advantage of doing it from an observational perspective with a nice, simple phenomenological model,
Yes.
that we can sweep a lot of that under the carpet, and we'll leave that to the people who really do that stuff very well to say, oh, these are the precise details of what we think is going on. But we have a viable physical model, and which it gives us tests, and we say we think something like this has happened, and then you can say why it's not, because it's more sophisticated than what we're saying. But yes, I mean, it's if you had previously asked me what's one of the hardest areas of things you may be looking for phenomena in, and what sort of phenomena, if you'd said merging black holes in an accretion disk of a supermassive black hole, I mean, the only thing that would make it harder is if there was a very large radio jet there as well, and this was a blaze off, because that's then even more complicated. But yes, you're right. I mean, conceptually, this is the sort of the intersection of several circles in a Venn diagram of the difficult bits of astrophysics.
Right, right. Yes, all the difficult bits. But this is amazing research. I am so very pleased that you were able to look at all those transients, come up with a theory, and then so rapidly after LIGO started functioning, make this discovery.
We were really surprised. We thought we would be doing a statistical survey to
Yeah.
say there's a slight excess of things happening here, rather than actually going, oh, here it is.
Well, this is amazing. And where can people go if they want to follow your research and keep track of, well, these discoveries as they come in the future?
So, one, if you're interested generally in time domain astronomy, I would suggest going to the Zwicky Transient Facility webpage on the Caltech website. So it's ztf.caltech.edu. Any of the discoveries we're making, not only with supermassive black holes, but with supernovae and new types of asteroids and all that sort of thing, gets posted there. So I think that's a good place to follow future developments.
That sounds great. I know we've covered things from ZTF before, and I look forward to covering more of them in the future. Now, we covered a whole lot of ground today. If
Yeah.
people only hold on to one idea from today's discussion, what one thing do you want them to remember?
What I would say is that this is the first time we've seen as well as heard the merging of two black holes. I think that's just the sort of soundbite thing of what's going on, and that's just so cool.
And it's the thunder before the lightning.
Yes, yes, indeed.
Well, this has been absolutely amazing. Can you say that website one more time?
Yes, it's ztf.caltech.edu.
All right, Matthew. This has been amazing. Thank you so much for joining us today. And thank you everyone out in the audience for being with us here as we bring you amazing light getting shocked into existence through merging black holes.